I asked ChatGPT if it understood undergraduate real analysis. And when it assured me that it did, I decided to put that to the test. I had it prepare a comprehensive final exam for undergraduate analysis. And then, after verifying that all of the questions were well written and solvable, I turned it right around and asked it to solve its own exam. Here's how it went. All right, here are ChatGPT's answers. I'm ready to take a look. Let's see how well it does. Sequences and limits, first question. Does the sequence an converge, where an is defined as minus 1 to the n times n over n plus 1? Well, the answer is going to be no on this one. Let's see what ChatGPT says. To analyze the limit as n goes to infinity, observe that limit as n goes to infinity of minus 1 to the n times n over n plus 1 equals limit as n goes to infinity of minus 1 to the n times n over n plus 1. The second factor converges to 1 as n goes to infinity, and the first factor alternates between minus 1 and 1 because of minus 1 to the n. Thank you for defining that for us. Therefore, the sequence does not converge as it oscillates between two values. I think I would give this full points. It does sound as if they understand what they're talking about when it comes to convergence of a sequence, that when it oscillates between these two values, minus 1 and 1, this is just not going to be convergent. And they did isolate that n over n plus 1 is going to 1 as n approaches infinity, which causes the sequence to effectively just be minus 1 to the n as n gets large. So good job on that one. Is an bounded? Yes, the sequence is bounded. For large n, the term n over n plus 1 is approximately 1. So the terms minus 1 to the n or n over n plus 1 oscillate between values close to 1 and minus 1. Hence, the sequence is bounded by minus 1 and 1. Another great answer. I think ChatGPT gets full marks on this first question. Let's move on. Completeness of R. Show that A, given by x and q where x squared is less than 2, is bounded above in Q, the rationals. Okay, the set A consists of rational numbers whose squares are less than 2. Good start. Clearly, A is bounded above because for any x in A, x squared is less than 2, so x is less than square root of 2. Perfect. However, square root of 2 is not in Q, so the least upper bound is root 2, which is an irrational number. Thus, the set is bounded above, but the supremum of A is not in Q. I think this was for the next question. There's also some things that I want to pick apart about this. I would be a little bit concerned if someone actually wrote this down on a problem, but the first part of their explanation, ChatGPT, perfect once again. That x squared is less than 2, so x is less than the square root of 2, the positive square root of 2, and it is bounded by negative root 2 and positive root 2 in the rationals, so it is bounded above. Good answer. B, prove that supremum of A does not exist in Q, but does in R. Since supremum of A equals square root of 2, not in Q, there is no rational supremum for A. However, R is complete, so the supremum of A in R is square root of 2. Okay. Coupling that with kind of this winding argument that they made earlier, this to me sounds like they don't have a good understanding of what a supremum is. I would really prefer that they were to show what a supremum actually is by demonstrating it using some sort of analysis. And the way we would want to do that on this one is to first demonstrate that square root of 2 is in fact a supremum for the set. And that's pretty straightforward. It is bounded above. But then the supremum has to be the least upper bound. So we need to show that any other lower upper bound than root 2 actually is surpassed by an element of the set. And currently they have not done that. The way that we would go about this is by invoking the density of the rationals in the real numbers. So suppose that there was some rational number or real number, for that matter, that was less than the square root of 2, which was also an upper bound for the set A, then there would exist a rational number between that supposed lower upper bound and square root of 2, therefore contradicting our assumption that we have a lower upper bound. So just some arguments such as that would be simple enough to demonstrate that they understood what was going on here. They say, however, R is complete, so the supremum of A in R is the square root of 2. I think I might give them full marks for this. So I would definitely count off on this question that they didn't really demonstrate that they understood what a supremum is. But invoking on the completeness of R, which of course is kind of given at the headline of the question, they did a decent job of showing that there is a supremum in the real numbers. I would still prefer that they went through that argument about what the supremum was, but if they were to do that for showing that it doesn't exist in the rationals, then I would have given them full credit for this as well. So I don't think they did a good job on this question. I would probably give them maybe 1 or 2 points out of however much this is worth, maybe 5. So maybe I'll give them a 6 out of 10 on this question. So not a great start on the second question. Let's continue on. Cauchy sequences. I think we were asked to define what a Cauchy sequence is. So it looks like this is their definition. A sequence AN is Cauchy if for every epsilon greater than 0, there exists a natural number n such that for all m and n greater than or equal to that value, the difference between subsequent terms, well, not necessarily subsequent, but any two terms in the sequence is less than the epsilon that we were given at the start. So we choose n based on epsilon, and then we need all of the terms beyond that mark in our sequence to be within epsilon of each other. And this makes sense for Cauchy sequences, which are convergent. So that is the definition. Well done on regurgitating that from their memory or possibly pulling it off Wikipedia on the internet. Now we're asked, prove or disprove every Cauchy sequence of rational numbers converges in Q. And I thought that this was a very interesting question because remember, we just demonstrated that there is a rational sequence of numbers that converges to an irrational number, square root of 2 in the previous problem. There's a supremum that does not exist in the rationals in that previous set. So this is false. Good start. The rational numbers Q are not complete. Okay. For example, the sequence AN equals 1 plus 1 over n is Cauchy in Q, but converges to 1, which is irrational. No. Therefore, a Cauchy sequence of rational numbers may not have a limit in Q, although it will have a limit in R. Okay. Oh boy. Well, they got the answer right, and this last statement makes me think that they've probably kind of memorized something in their notes somewhere, saying that a Cauchy sequence may not have a limit in Q, but it does in R. But it feels like they've completely missed the concept, and especially with this question coming directly after the previous question, where we were asked to prove such a thing, that the supremum of A does not exist in Q but does in R. I think there is a lack of understanding on this one. So I will give them 3 out of 10 points for saying this is false, which is the correct answer, and for kind of demonstrating that they have some knowledge, at least, of Cauchy sequences and convergence, but they did not do a very good job of giving an example. A simple example, I think, often is going to be any sort of irrational number. You could write out the irrational number as a string of decimals, which would go on infinitely, but for an infinite sequence, we could represent our sequence terms as just adding one extra decimal place. So For example, if you wanted to do E, it would be 2, and then 2.7, and then 2.7, 1. I'm blanking on E for a second. I think it's 2.718 or something like that. But yeah, that would be a good example. I think there's plenty of others that you can demonstrate. I'm sure that there are some in almost any real analysis textbook that would be a little bit cleaner. But giving an example, or at least making a note that we had just proved something similar in the previous question, would be enough to earn full marks here. So not a good start for ChatGPT. Let's see if it does better. We're given the function f of x, which equals x sine 1 over x for x non-zero, and it's 0 at x equals 0. Prove that f is continuous at x equals 0, but not differentiable at x equals 0. This is a classic calculus question. So how do we do this using our analysis techniques? Well, we need to show that the limit as x approaches 0 of f of x equals f of 0. That is correct. For continuity, that's all we need to do. And here, f of 0 is just 0, as defined. So we want both the positive and negative limits as it converges from both sides of x sine 1 over x to approach 0. For x non-zero, we have f of x equals x sine 1 over x. Since sine 1 over x is bounded between -1 and 1, we know that the negative absolute value of x, less than or equal to f of x, less than or equal to absolute value of x for all x in the range, and specifically as x goes to 0. Thus, the limit as x goes to 0 of f of x equals 0 equals f of 0, so f is continuous at x equals 0. If I wanted to be nitpicky about this answer, I would probably say that they didn't really connect these last two steps, that once we have this, we can utilize, I think it's called the squeeze theorem, and take the limit of both of these outer parts, show that the limit as minus absolute value of x goes to 0 as x goes to 0, and similarly for the top end. Therefore, the limit as f of x goes to 0 is also 0. But it looks like they understand what they're doing, so I'm not going to take points off on that one. So this, I would say, was very well done, well reasoned, and they come up with a solid answer. So full marks for that. Differentiability. We check the definition of the derivative at x equals 0, which is f prime of 0 equals the limit as h goes to 0 of f of h minus f of 0 over h minus 0, which equals the limit as h goes to 0 of h sine 1 over h, which equals the limit as h goes to 0 of sine of 1 over h. Since sine of 1 over h oscillates between -1 and 1 as h goes to 0, the limit does not exist, so f is not differentiable at x equals 0. Yeah, I mean, maybe they could have been a little more explicit about what they meant by sine of 1 over h oscillates between -1 and 1, but I think this is a solid enough answer that I will also give this one full marks. So congratulations, 10 out of 10 on that problem. Let's keep going. Uniform continuity. Let f of x equals 1 over x on the interval 0 to 1. The open interval. Is f uniformly continuous on 0 to 1? Well, no. Let's see what ChatGPT says. No. Good start. F of x equals 1 over x is not uniformly continuous on 0, 1. As x approaches 0, the values of f of x become arbitrarily large. And for any delta greater than 0, we can find points x1 and x2 close enough to 0 such that the difference between f of x1 and f of x2 exceeds any fixed epsilon greater than 0. Thus, f is not uniformly continuous. Okay, this is really good understanding of what uniform continuity means. It looks like without stating the definition of what uniform continuity is, they gave all of the key pieces. So the deal with uniform continuity is that given an epsilon greater than 0, which they mention right here in their argument, we should be able to find a delta greater than 0 that no matter where we are on the domain of the function, points x1 and x2 will always be a distance less than epsilon apart if they, in proximity, are less than delta themselves on the x-axis. So the issue here that they're alluding to is that because near 0, f of x is quite large, given epsilon, no matter what delta we choose, we can always just shift our points closer and closer and closer to x equals 0. And the difference between two values on the x-axis, the value of the function, 1 over x, for those two values, when they are arbitrarily close together, we can make that as large as possible. And that's what their argument is. And for this argument, I think I would give them at least 8 out of 10 points because they did a really, really good job. I'll even give them 9 out of 10. What I would really like to see on this problem, though, is some actual calculations being performed. Do a little bit of algebra to actually demonstrate that you can do this regardless of what epsilon and delta are chosen. And it wouldn't be that difficult. You would just have to probably choose points that are, you know, maybe less than 1 over delta, or less than delta, for example, apart on the x-axis, and or less than delta away from 0, basically, so that the values are going to be so large that f of x1 minus f of x2 is going to be greater than epsilon. But that would be the idea. So I think I would really prefer to see a little bit of algebra worked out on this one. But 9 out of 10, not bad. They at least understood what they were trying to show. Compactness. I think we were asked to show the Heine-Borel theorem and if that was what the definition was. So the Heine-Borel theorem said a subset of R is compact if and only if it is closed and bounded. Very important in almost any analysis class moving forward. We're given the set 0, 1, half open, union with the point 2. Is it compact? The set is not compact because it is not closed. The point 1 is a limit point of the set 0, 1, but 1 is not in 0, 1 with the open interval on the right end. Therefore, the set is not closed and hence not compact. This is perfect. I mean, this is exactly what you want to see. So they got the definition of Heine-Borel correct, and then they mentioned that 1 is a limit point of the set, and for a set to be closed, it has to contain all of its limit points. I think we see that later in the quiz. So this is exactly the answer I would like to see, and well done, 10 out of 10. Let's go on to question 7. State and prove the mean value theorem. Okay. The mean value theorem states that if f is continuous on AB, closed interval, and differentiable on the open interval, AB, then there exists a point C in the open interval such that the derivative at that point equals the average rate of change over the interval, f of b minus f of a over b minus a. And this is perfect, great statement of the mean value theorem. And I think it's really important to kind of break down what these terms are, because as mentioned, the derivative at some point equals the average rate of change on this interval, f of b minus f of a over b minus a. You'll probably be familiar with this from like high school algebra class, that this is the rate of change along an interval. It's basically the slope between the values of the function f at the endpoints. Example. Okay, state and prove the mean value theorem. We got halfway there. So the statement is good. They regurgitated all of that information correctly, but I don't see a proof. I think then we were asked to come up with an example. Is that correct? Yes. Let's take a look at their example, and then we'll maybe talk a little bit about the proof, but it looks like they just didn't give one, so we'll mark them down for that. Let f of x equals x squared on the closed interval 1 to 3. By the mean value theorem, there exists a point C in 1 to 3 such that f prime of C equals f of 3 minus f of 1 over 3 minus 1, which equals 4. The derivative, f prime of x equals 2x, for f of x equals x squared. Good. So c equals 2 satisfies f prime of 2 equals 4, which is equal to the average rate of change over the interval. So that is perfect. But I think the main point of this question would have been the proof. At least for most real analysis classes, we focus on proofs. It's not just about regurgitating information and stating theorems. While theorems are important, and understanding the motivation of the theorem is also important, we really do care if you're able to apply some of the techniques that we've used in analysis to prove some of these ideas, because that's mostly what analysis is going to be about moving forward, is utilizing elements of compactness, supremum, infimum, convergence, uniform continuity, all of these things. You're going to learn a lot more if you continue on into graduate level education. So I have a hard time giving this more than 5 out of 10. And I think I will give it a 5 out of 10 just to be generous. They did state the theorem. They did demonstrate it with an application. But the proof is just completely missing. So the proof of the mean value theorem often relies on something else that I think is known as Rolle's theorem, which is essentially that if f of b and f of a are the same value, so their difference is 0, then there exists a point in the open interval between them such that the derivative is 0. And usually the mean value theorem is proved using this idea. And the way to do it is to try and redefine a new function, let's call it g instead of f, such that the endpoints of g have value 0. And to do that, we're going to subtract the average rate of change times the distance traveled from f of a. So this would be this entire value, which is just a constant, f of b minus f of a over b minus a, times x. So we'll write g of x equals f of x minus f of b minus f of a over b minus a times x. And this means that throughout the entire interval, once we travel the distance of b minus a, it's going to have the effect that our endpoints of our interval are going to have a slope of 0. Then we apply Rolle's theorem, and with a little bit of algebra, we can then prove the mean value theorem using that. So that's the idea. 5 out of 10 points for ChatGPT on this one. Let's move on. Riemann integrability. We are given the Dirichlet function, which is that f of x is 1 for x being a rational number and 0 if x is irrational on the closed interval 0 to 1. Is f Riemann integrable? Now, this is a fun question because for those who are graduate students, you would maybe say yes on this one. But no, f is not Riemann integrable. The function is discontinuous everywhere on 0, 1 because q is dense in R. And a function with too many discontinuities can't be Riemann integrable. Specifically, the set of discontinuities is not of measure 0, so f is not Riemann integrable. Okay. I don't know if undergraduates learn the concept of measure. This is one of the first things you would learn in a graduate course in real analysis. I'm sure that some institutions would teach measure theory to undergraduates in their analysis course, or maybe even just mention it. But yes, this is basically the reason why f is not Riemann integrable, is that it has too many discontinuities. Now, the function being discontinuous everywhere because q is dense in R, I guess technically applies, but I suppose the real problem is that q and the irrationals, sometimes represented as bold I, are both dense in R. So this is why the function is discontinuous everywhere, not just because q is dense. I I guess I would give this full credit because this last sentence certainly sums up when functions are and are not Riemann integrable. It feels like there was a bit of confusion about why there were infinitely many discontinuities, specifically a non-zero measure of discontinuities. In fact, it is measure 1. But yeah, I think I would give this full credit because certainly this last sentence defines exactly what the reason is. Now, for those of you who do go on to graduate analysis, this measure theory that I've mentioned will lead to a new form of integration, which is a little bit more powerful, called Lebesgue integration. And in Lebesgue integration, this function is integrable, and it would evaluate to 0, the integral over this closed interval for this function. And I guess I'll probably cut myself off there before diving too deep. But if you're curious about it, look up measure theory or Lebesgue integration. So on to number 9. Did I say what I was going to give them? 10 out of 10. Good answer. Pointwise versus uniform convergence. We are given the sequence fn of x equals x to the n on the closed interval 0 to 1. Does fn converge pointwise or uniformly on 0, 1? Well, pointwise it does, but uniformly it does not. So let's see what ChatGPT says. Pointwise, for x in 0, 1, half open, fn of x goes to 0 as n goes to infinity, and for x equals 1, fn of 1 equals 1 for all n. So the sequence converges pointwise to the function here. I think this is actually good enough. They clearly knew what they were working towards, and sure, I mean, maybe we could be a little bit nitpicky about them proving that in the half-open interval that fn of x does converge to 0 for all x, but hopefully that's something that you can learn from these powers, that x to the n, as long as x is less than 1, goes to 0 as n goes to infinity. Uniformly, to check if the convergence is uniform, observe that for x close to 1, fn of x does not converge to 0 uniformly because the convergence is slow near 1. This is not a math term. The convergence is slow. Thus, fn does not converge uniformly on 0, 1. So they got the answer right. I think I'll probably give them 2 points for that. So 2 out of the 5 for this second half of the question. But I don't feel like they did a good job of defining why it doesn't converge uniformly. They didn't use the definition of uniform convergence. So I don't think I'm going to give them credit at all for their explanation. I mean, the convergence is slow near 1. Even if they had said something like values close to 1, values close to x equals 1 still remain close to y equals 1 or f of x equals 1 for large n, that would be a nice way to frame it. The way uniform convergence works, of course, if you're not familiar with the definition, is that given epsilon greater than 0, we want all of the functions beyond a particular starting point in the naturals. So for n greater than or equal to some large value, let's call it 1,000,000 or something, or 1,000,000,000. I mean, you pick. We want to be able to choose a natural number n given this epsilon such that the value of every function beyond that point is always going to be within epsilon. And so they kind of got close to this idea when they said for x close to 1, the convergence is slow near 1. What they meant was that the convergence to 0, f of x equals 0, is quite slow. So, for x equals 0.999999999, it's going to take quite a long time for this exponent, 0.9999 to the n, to converge to 0. And therefore, given an epsilon, whatever n we think is going to be large enough, we can just choose a point that's like closer and closer and closer to x equals 1, and it's going to be further than epsilon away from x equals 0, or f of x equals 0. So the convergence is not uniform. I'll give them 7 out of 10 for this question. Last question about metric spaces. A set A as subset of X is closed if it contains all its limit points. Was this the question? The question was, define what it means for a subset to be closed. Okay, so a subset of X is closed if it contains all its limit points, i.e., if X is in the closure of A, this is the shorthand for that, and Xn is contained in A, converges to X, then X is an element of A. Perfect. That is exactly what it means for a set to be closed. It contains all of its limit points. I think this is a great definition. So we didn't utilize anything such as the distance metric, which often is going to be necessary in some of these proofs for metric spaces. But I don't think we need to for defining what a closed set is here. Prove that every convergent sequence in X has its limit in the closure of its range. So this is basically by definition, I think. Let xn approaches X in a metric space X, with xn being an A for all n. Since the sequence goes to X, X is a limit point of set A, meaning X is in the closure of A, which is the closure of A. Great. I'm glad they reiterated the explanation of the closure of A multiple times. Hence, the limit of a convergent sequence lies in the closure of the range of its sequence. Again, this was not too challenging of a problem. I think this was basically just unpacking the definition of closure and convergent in the metric space. Maybe once again, we could ask them to be a little bit more explicit about using the distance metric, stating that given epsilon greater than 0, the distance between xn and x is always within epsilon because of the Cauchy sequence, the Cauchy criterion for convergence. And then that would be another way to show that the this converges to a limit point, and because the space is closed, or because it would be in the closure of the range, therefore that proves it. So ultimately 10 out of 10 on this one. And so how did they end up doing? I mean, ultimately not too bad. There were quite a few of these problems that they got completely correct. And there were a couple that I think they overlooked, such as state and prove the mean value theorem. They just forgot to write the proof. But it does seem like ChatGPT has some understanding of undergraduate real analysis.